Hello everyone, I hope you are doing good. So in today's video, I'm going to talk about how we will be able to connect Python with Aspen Hysys. And in this video, I highly recommend to go and check out this GitHub repository, which is shown here. I will mention this repository in the description down below. So please feel free to go and check out this repository. It is very useful. Um, for connection between Hysys and Python. So basically, there are a bunch of files which are the few files that are very important in this tutorial. The first file is Hysys underscore Python underscore spreadsheet.py. This is a Python file. The other Python file is test underscore one.python. This is a second Python file. These two Python files, and then there's a Hysys file, which is the example of Hysys simulation, which we are going to connect with Python. So I already downloaded that one. If you you need to go to the code and you can download as a zip, or if you want to make a clone of this one, then you can copy this one, copy this link, and then you can make a clone in VS Code, and then you can use in both ways. I already downloaded this one in one of the folder which I want to open using VS Code. Before I talk about this Python file, I just want to show you the simulation file, and I will explain to you what we are trying to simulate today. So this is a kind of example that we are going to connect with Python. So if you look at the feed stream, in the feed stream we have this the temperature is 30 degrees Celsius, and the pressure is about 506 kilopascal, and the flow rate about 100 kgmol per hour, with the composition of these components: methane, isopentane, NC12, CO2, water, oxygen, and nitrogen, where methane, isopentane, and NC12 are used as a reactants, and the remaining as a product, which will be later on you can see in the products. So this stream at temperature about 30 degrees Celsius is first cooled down using a cooler to approximately 15 degrees Celsius. And if you look at the flow rate is about 100 kgmol per hour approximately. It is went to the flash drum, where you are getting a product of gas phase and the liquid stream. So let's talk about first the liquid stream. So if you look at the liquid stream, we have mostly that is separated is NC12, which is 47 out from 100 kgmol. 47 kgmol is NC12 that is separated in the liquid stream, and then isopentane, which is 22 kgmol per hour, is also separated in the liquid stream. And a very small amount of methane, which is about 1.67 kgmol per hour, is separated in the liquid stream. So this liquid stream, which is at 455.9 kilopascal, is need to be reduced in pressure. Once the pressure is reduced to approximately 101.3 kgmol, which is about 1 bar and approximately 1 atmospheric pressure, is sent to a distillation column. The distillation column is running with the total number of stages is 20. The feed location is in the middle, right in the middle, 10th stage. And the distillation column is running partial. The condenser is running partially, which means like partially it is we are getting product as a gas phase, and partially we are getting product as a distillate. The column is operating at 1 atmospheric pressure from top to bottom, and with this conditions in the distillation column, we are separating the product into three different products. For example, the light gas stream, which is on the top, then we have a distillate, and then we have the product in the bottom stream. If you go and check the bottom product, which we are assuming that we are getting a large amount of C12 fraction, which is the you can see here we are getting approximately 47.914 kgmol per hour of NC12, and a very small amount of isopentane that is also separated here. Where in the distillate, if you look at the distillate, if you look at the bases into mole flows, approximately 21 kgmol of isopentane is separated as a distillate, and a very small amount of methane is also recovered here, whereas in the light gas we are expecting methane. It's a large amount of methane that will be recovered. So if you look at here, you can see here 1.5597 kgmole is recovered on the top and very small on the bottom. Methane in the feed is already very small amount, that's why you can see a very small amount of fraction of methane that is recovered. So if you check the feed composition, you can see we have 28 kgmole which is recovered in this particular case, and the rest of the methane which we are expecting to get is off gases on the top. So if you talk about the gas phase, this one is finished. The liquid phase, this is the liquid stream. And for the gas stream, if you look at the gas stream and if you check the composition of the gas stream, we are expecting mostly methane and mostly methane, which is 27 kgmole, small amount of isopentane. And if you look at this gas is need to be heated to a temperature about 350 degrees Celsius before it is sent to a reactor. This reactor is the reaction between air and the gases, and after the reaction we are getting two products. One is a liquid, one is a stack gases. So if you look at the liquid product, this will contains mostly the products of the reactions. You can see here because most of the reaction in this particular case is a gas phase reaction, so we are not getting any liquid as a product. Whereas if you look at the gas stream, and if you look at the composition of the gas stream, we are getting 33 kgmole of carbon dioxide, 59 kgmole of water, and then we are getting 237 kgmole of nitrogen. Nitrogen is used as an inert gas in this, and there's no participation in the reaction, so it is used, whatever is entered, it is leaved, it is coming out as it is. And a very small amount of methane is also produced here. These gases need to be the pressure of these gases need to be decreased, because if you look at the pressure here is 405 kilopascal, need to be reduced to 1 atmospheric pressure before it is sent off to the atmosphere. And in this simulation we have three spreadsheets. One of them is used for the flash. If you open the flash spreadsheet, you can see here we are using a flash temperature above 15 degrees Celsius, and we are using a mass flow, gas mass flow rate, which is 545 kg per hour, which is this one here. And if you open the turbine stream also have two information. One is for the efficiency, which is adiabatic efficiency of 85%, and the energy generation in kilojoule per second, which is 2020 kilojoule per second. This will show the information of turbine. Then we have the spreadsheet for the distillation column, which will again show you the boiler energy, condenser energy, and the reboiler energy, which is if we talk about condenser is 663 kilojoule per second, and for the reboiler it is 1660 kilojoule per second. So this is regarding the flow sheet. This flow sheet need to be connected to the Python, and then we will try to extract the information from this from these three spreadsheets on the Python, and then we can plot there. So let's first open up the Python. In the Python, there are two Python files that is important in this tutorial. The first one is Hysys _Python _spreadsheet. If you open that one, we have some. We need to import some important information. For example, in this case, we are importing the OS, which is importing operating system interface. Then we have the COM, the communication port, which in this case we are using win32 com.client as win32. These two informations are very important. After that, we are creating a function In this function we are taking some information. We are taking a file name, which is the Hysys file name. We are taking the information for the spreadsheet that is used in the Hysys file name. Then we have different operations that is used in the Hysys file, and then we need to check either it is visible or it is not visible. So 1 is showing that it is visible and 0 is showing it is not visible, and the active is showing the solver either the solver is active or not active. Here some information is providing regarding what we are using in this function. So we have file name, which is a string, and for example in this case we are using test.hsc, spreadsheet which is a tuple, and the spreadsheet also, which is the spreadsheet that is used inside these Hysys files. Then we have unit operations which are used in the Hysys files. So there are quite few unit operations that we are using, and we need to extract the information. Then for the visibility, we need to it is an integer, and we need to check 1 for visible and 0 for not visible. And then for the active, again it is an integer which is showing 1 for for active simulation and 0 for not active information. And the output from this simulation is a class of Hysys which contain valuable information, which I will talk about just now. So for example here we need to take the Hysys file by using this line of code, and then we need to print this one, and we need to wait for a second until the Hysys file is open. So here it is showing the print function, which is showing basically to open the Hysys file. Then we need to open the Hysys application. Once the Hysys application is open, it is assigned to HyApp and then we need to check if it is active. If it is not active, then we need to open it, and if it is active, then we need to open the document, the active document, the active simulation that we are basically trying to connect. Otherwise, if these two conditions are not met, then they will give us the exception, which is argument for input variable is active is not valid. So this one is try to avoid any complications later on. If we are having some problem connecting. So then we need to open the Hysys environment. Then we need to get the title of the file. We need to write down the title of the file in program. Then we need to open the property package. We need to mention the which property package that we are using. We print out the property package. So in this particular case, we need to find out all the spreadsheet that is present inside the Aspen Hysys file. So for this one is using a for loop to check the spreadsheet in the Hysys file and try to assign that spreadsheet to this dictionary. So we are trying to populate all the spreadsheet to this dictionary by using this for loop. Then we need to check solver. Solver command is used basically to assign the solver to this particular variable, constant you can say. Then we need to extract the material streams and energy streams by using this line of code from the Aspen file. And then we need to extract all the unit operation that we are running in Aspen file by using again we need to give an empty dictionary, and then we need to extract the dictionary and populate that unit operations to this dictionary. So lastly, what we are trying to extract all of this, we need to collect all this information in a class, and the class name is Hysys. We pass on all the information that we are collected on the top. So for example, in this case, the dictionary for for all the spreadsheets. Then we have a solver. Then we have material stream and energy stream. Then finally we have the unit operation. All of them will be shown pass on to this class, and we can just print out all the information, and then we can return that class, Hysys class, in this in this file. So this is regarding the first file, which is important, the Python file, which contains the function. The second test Python file here is the main file, which is basically used to get all the information. So the function that we have generated in this file, first we need to import. So this is the file that the second file that we need to import, and this is the function that we have created. We import some libraries like NumPy, we matplotlib for plotting and time. And then first we need to assign the Hysys file to this file, and then we have all the spreadsheets that is used in a Hysys file. We need to create the names and we need to assign this to spreadsheet, and similarly all the unit operation that we are using inside the simulation we need to assign to the units. After that we need to perform some connection. So again we are assigning test_1 to, and we need to use the function that is built inside this file. Aspen connection, we need to assign, we need to input some information which is we already generated, file, spreadsheet and units. And from this we need to extract the turbine information, the turbine Excel sheet. And from this turbine Excel sheet we need to extract the efficiency, which if I open this one I will show you. So this is my file. There are some issues, otherwise I will show you something. My cursor is not available. Anyways, I just want to open the Python file. So here you can see we are extracting the turbine information and all the cells of the turbine which contain efficiency and the power, the generation, which we extract and assign to efficiency and generation. Then from here we need to assign the efficiency values to this constant, and then the solver we need to assign to solver. We need to print this the initial efficiency that we have just extracted from the simulation, and we need to use this one to iterate. So let's say we have 10 points and we need to create 10 different efficiencies and generations, and we need to plot this one using matplotlib. Here in this particular case we are using a for loop command to iterate through all the points. Using initial value efficiency, we need to assign the initial value efficiency, and we need to save this one in if list. And similarly generation is also is saved in the generation term, and similarly all these efficiencies are now need to be assigned, need to be iterated by adding one into this efficiency, and then same thing is again looped through all of these efficiencies. We need to generate some data. In this particular case we need to assign the X label, we need to assign the we need to assign the labels X label, Y label, and then title of the plot. And similarly we need to use the same information here, try to get 10 different efficiencies, 10 different generations, and assigning the first value of efficiency to this for loop, and then we are going through this for loop and try to run the simulation and try to extract and populate the data in the list into efficiency and generation. After that, when we get all the data, we need to plot the efficiency versus generation, and the labels we can label X label is turbine efficiency, Y label is energy generation in kilojoule per second, and then we have a title of it in solver. So what we are doing in this particular case is, if you look at here, we are waiting here for the solver to solve, and on the top we are not waiting for the solver to stop, and we are just continue like this. Whereas in this particular case we are allow the solver to stop for a while and then populate and then plot the diagram. So these are the two files that is important. Let's go and run this file. If you just click on the run button, sorry, I think this is a problem with the cursor. So if you run this one, it will take some time and will generate this plot. On your left hand side we have the plot between energy generation and the turbine efficiency. This is showing without waiting for the solver. You can see we have only getting one dot, 1 point, and if you wait for the solver to solve in between the iteration, if it is stopping for a while and then is generating the information, you can see we have a bunch of data which is showing that the efficiency, if increases, it also increases the energy generation. Or otherwise, if the energy generations are increased, it will increase the efficiency in the turbine. So this basically this is the end of this tutorial. The main purpose of this tutorial is to attach this simulation to Python using some Python functions, a Python function, and then the main Python file. So if you have any questions in this regarding this video, and if you are facing any problem, please do mention in the comments down below. I will be happy to answer all those questions. Thank you very much for listening to me. Have a nice day. Take care and bye.